Okay, let's solve this inexact differential equation by getting the general solution. So before that, we know that the general equation of the first order differential equation is m dx plus n dy equals 0. So before, I am going to test if this dE is really inexact. So by first, I'm going to identify what is m. So m is 2x squared y minus 2y squared plus 2xy, and our n is x squared minus 2y. Now, to test if this dE is really exact, what are we going to use is this formula. The partial derivative of m respect to partial derivative of y is equals to partial derivative of n respect to partial derivative of x. That's our goal if the dE is exact. If they are not equal, then it is inexact or non-exact dE. So let us solve for the partial derivative of m respect to partial derivative of y is 2x squared minus 4y plus 2x. And for the partial derivative of n respect to partial derivative of x is 2x minus 0, or simply 2x. Now as you can see, they are not equal, therefore our dE is inexact. So to solve for the general solution of our inexact dE, we must use this first condition formula, which is 1 over n multiplied by the partial derivative of n respect to partial derivative of y minus partial derivative of n respect to partial derivative of x is equal to f of x. After solving for the f of x, you must solve for the integrating factor to convert the inexact dE to exact dE. So this is the formula after solving for the f of x. Then we get our integrating factor. Okay, let me simply copy the n and the dm and then the dx. I mean the partial derivative m and the partial derivative n. Okay. So our n is x squared minus 2y. Okay, our n is x squared minus 2y. 1 over x squared minus 2y multiplied by, okay, 1 over x squared minus 2y multiplied by, our m is a partial derivative of m is 2x squared minus 4y plus 2x. Okay, 2x squared minus 4y plus 2x, and our partial derivative of n is 2x minus 2x since this is the formula. Okay, then we solve for f of x. F of x meaning we must get only in terms of x. If we do not get in terms of f of x, there is y included, then we solve for the second condition, which is, I did not write the formula for the second condition, so never mind, let's just continue. Okay, this 2x minus 2x is cancelled, then common factor 2, we let 2 out, it is a common factor, all over x squared minus 2y and f of x. So simply our f of x is just 2. Okay, now we solve for our integrating factor. E to the power of the integral of f of x is, this is the formula, our f of x is 2, then we place 2 here, and then dx. Now our integrating factor is, e to the 2x. Now what are we going to do with this? Our integrating factor is to multiply by our original differential equation to convert the inexact dE to exact dE. Okay, let me copy the original dE. Okay, now we multiply both sides by e to the x, then we get, okay, we get 2x squared y e to the 2x. Wait, let me make it smaller. Okay, 2x squared y e to the 2x minus 2y squared e to the 2x plus 2xy e to the 2x dx. Wait, this is just long. Let me move it a little bit. Okay, there. Dx, and then x squared e to the 2x minus 2y e to the 2x divided by dy. And I can just put here the equal 0. Since we're short on space, I can make it smaller. There we go. And then equals 0. Then after multiplying both sides by our integrating factor, then let us test if it is really true. We converted the inexact to exact dE. Now again, for the test of exactness, we remember that this is our general equation. M dx plus n dy equals 0. We know that this is our m and this is our n. Now we get the partial derivative of m respect to partial derivative of y. Okay, our partial derivative of m is, since this is respect to partial derivative y, we eliminate y. And treating the x terms as constant, since it's respect to partial derivative of y, then this will be 4y e to the 2x plus 2x e to the 2x. Now we solve for the partial derivative of n, respect to partial derivative of x. Since partial derivative of x, we treat the y term as constant. Since it is x squared multiplied by e to the 2x, this is the derivative product rule. Then we get, we get 2x e to the 2x plus, never mind, sorry, I planning to do a shortcut, but never mind, let's just do it step by step. So e to the 2x times 2x plus x squared times 2e to the 2x minus 2e to the 2x. Okay, and wait, I'm wrong here in this part. Since with respect to partial derivative of x, we get 4y e to the 2x. Okay, so for the further simplification, our partial derivative n is 2x e to the 2x plus 2x squared e to the 2x minus 4y e to the 2x. Okay, now comparing to our partial derivative of m respect partial derivative of y, here, as you can see, it is the same. Okay, wait, they are equal, which means our dE is now exact. Our new differential equation is now exact. Okay, let me copy this to solve for the general equation. Okay, so, let me copy. Okay, for the formula of the general solution, this is the result of exactness. Since our dE is now exact, this is the formula to solve for the general solution. Integral of m partial derivative of x plus g of y, and f2 is equals f sub 2 is equals to n and partial derivative of y. That is partial derivative of x, then plus f of x. Now, and then let us just solve this first before after solving for the f1, f sub 1, f sub 2, we get then f r x in terms of x and y plus f of x plus g of y. Okay, then let us solve now for the f1. Note that after solving for the f sub 1 and f sub 2, we plug in to our general solution, which is f is equal to r in terms of x and y plus f of x plus g of y. I'm gonna explain later why our general solution, I'm gonna explain later why it is in terms of x and y and plus f of x plus g of y. Okay, then let us solve for the f1. The integral of, okay, our m is, or let me just copy. Okay, partial derivative of x plus d of x, partial derivative of x plus gy. Wait, there's something missing. This is 2 and 2. Never mind, let me arrange this one. Okay, e to the 2x. It's right. Okay. So the first part, since it's partial derivative of x, the integral is first part. This means we use integration by parts, since in y term we treat as constant. Okay, by using this technique to solve it fast, is d and I for the first part. Our d is x squared, and our I is e to the 2x. Okay, then so x, derivative of x squared is 2x, and derivative of 2x is 2, and then 0. The integral of e to the 2x is 1/2 e to the 2x. So the integral, that is 1/4 e to the 2x, and 1/8 e to the 2x. So remember that we treat as 2 and y as constant. I mean, y treating as constant since it's the integral of this partial derivative of x. Then remember that we place here multiplied by our integration by part. Okay, then this is plus minus, plus and minus, multiplied by that, this by this, and this. Then this is gonna be x squared e to the 2x divided by 2 minus 2x 4 e to the 2x plus 2/8 e to the 2x. So that's our first part of integration. Let me resize there. Okay, then our second part, we, as you can see, it's no need by use by integration by part since we treat as y squared as constant. Then in the third part we treat y as constant. Then as you can see, it's x times e to the 2x. We use integration by parts again by this technique. I cannot use, but still we use the integral of u dv minus uv minus v du since it takes time and it takes space too. So let me just use this specific technique to solve it shortly and more space to save. Okay, then our g is x, I is e to the 2x, derivative of x is 1, and derivative of 1 is 0. And the integral of e to the 2x is 1/2 e to the 2x, and the integral of that is 1/4 e to the 2x. Remember that we treat 2y as constant. We make it the factored out. Plus minus plus. Okay, then we solve for the part, this part, and we get x half e to the 2x minus 1/4 e to the 2x. Then our third part is done. Then we can solve for the f1. Resize. Oh wait. Okay. So our f1 is if you see this first part of our integration, this is x squared y e to the 2x minus xy e to the 2x plus 1/2 y e to the 2x. So that's the first part. So for the second part, which is this one, the integral of that is simply y squared and e to the 2x. Okay, it is minus y squared e to the 2x. And then the third part is this one. It's this one. And then that is simply plus xy e to the 2x minus 1/2 y e to the 2x plus g of y. Okay, then we cancel the common and same signs in the same term, cancel terms. So we cancel this one, we cancel this one, and we only left by, so our f1 is x squared y e to the 2x minus y squared e to the 2x plus g of y. Now we got our f1. Then let us solve for the f2. So our n is this one. Let me copy. This is our n. Multiply by partial derivative of y. Okay. Plus f of x. Okay, the integral of this one multiplied by the partial derivative of y. Treating x as constant, then this is simply x squared y e to the 2x minus y squared e to the 2x plus f of x. Now we got our f1 and f2. After solving for the f sub 1 and f sub 2, we proceed to the result of exactness, or the general solution, which is f is equals to r in terms of x and y plus f of x plus g of y. So f is actually a constant for c, and r in terms of x and y, the meaning of r in terms of x and y is we plug in our equation in this f1 and f2. We plug in only, no wait, start to explain. We plug in the same terms, meaning the same phase in both f1 and f2. If f1 and f2, you did not notice that in terms of x and y, they're not the same. In comparing these both f sub 1 f sub 2, both this equation, you did not notice the same term in x and y, meaning there's something wrong with your solution. Okay, since as you can see, f1 and f2, they are the same, we simply copy our equation of the f sub 1 f sub 2, or neither of them. And you can choose whatever since it's the same. Let me copy or duplicate. And f of x and g of y, we find only in terms of x and only in terms of y, not multiplied by x and y, as you can see. And since f of x, we did not find only x terms, and g of y, we did not also find the in terms of y, meaning it is 0 plus 0 plus 0. And this is f. And then f is actually c, so therefore our general solution is x squared y e to the 2x minus y squared e to the 2x equals c. And that is our final answer for the general solution.